Hello and Assalamu alaikum. In today's lecture, we are going to discuss flags. Let's begin our lecture. Various arithmetic and logical instructions change the status of the flags, after which conditional instructions test the value of these flags to take control to the desired location. There is a list of flags which will be discussed one by one in this lecture. Do remember that initially all flags other than interrupt flag are 0. Let's start with overflow flag. Overflow flag indicates the overflow of leftmost bit of the data, that is sign bit, after a signed arithmetic operation. This flag is set to 1 when there is a signed overflow, and it is set to 0 when there is no overflow. To understand the working of overflow flag, remember two rules. Rule number 1. For addition, if both the sign bits of the given input data are same, that is 0 0 or 1 1, and the sign bit of the result after arithmetic operation is opposite to the input sign bit, then overflow flag is equals 1. So for the given rule, if the data is this and the operation to be performed is addition, then the result will be, in the given example, for addition, both the sign bits of the given data are 1 and the resultant sign bit achieved is 0, which is exactly the opposite of the given data. So this means overflow is equals 1. Let's consider another example. Now for the same addition operation, we have two 8 bits of data and the sign bit of both input is 0. Do remember the leftmost bit is considered as sign bit. So after addition, we get, just like the previous example, if you see over here, the sign bits of both the inputs is 0, while just like the previous example, if you check over here, the sign bits of both the inputs are 0, while the output achieved sign bit is 1, which is exactly the opposite of the given data. So in this example, again, overflow is equals 1. Now rule 2. For subtraction, if both sign bits of the given input data are different, that is sign bit of one input is 1 and the other is 0, and after arithmetic operation the input sign bit is disturbed, then overflow flag is equals to 1. Let's consider the following two examples. So example number 1. In this example, we are utilizing subtraction operator. So this will become, for the last bit, 0 minus 1 is not possible. So the above data, that is 0, will borrow from its base. So the base of binary is 2. So 2 minus 1, 1. As you can see that for this example, the sign bits of both data are different. One is 0 and the other one is 1. And after arithmetic operation, the sign bit of one data is disturbed. Initially it was 0 and now there is a borrow on this sign bit. So it means overflow exists. So overflow in this example is equals to 1. Let's consider another example. In this example, let's consider that we have the following data. And we are utilizing the same subtraction operator. So our result will be, as you can see that 0 minus 1 is not possible. So this 0 is going to borrow from this bit. So this bit will become 0 and it will give borrow to the next bit. So this will become 2 minus 1, 1, and 0 minus 0, 0. If you check initially, the sign bit of the data 1 was 1 and the sign bit of data 2 was 0. And during arithmetic operation, the sign bit is disturbed. Initially it was 1 and now the present value is 0. So it means that overflow flag for this example will also be equal to 1. Next is direction flag. This flag is specifically used in string instructions. If direction flag is set, that is the value of direction flag is 1, then the system accesses the string data from higher memory location towards the lower memory location, means in reverse direction. Let us consider this string. In the given string, A is at index 0, B is at index 1, C is at index 2. For direction flag equal to 1, the system will access this string in reverse order, that is from index 3 towards 0. So the access string will become D, C, B, A. You can set the value of direction flag to 1 by using a command std, where st stands for set and d stands for direction flag. Similarly, if the direction flag is reset, means the value of direction flag is equals 0, then the system will access the string data from lower memory location towards the higher memory location, means in forward direction. For example, for the given string, the system will access the string in the given order, that is A, B, C, D. In order to reset the direction flag, CLD instruction is utilized, where CL stands for clear and D stands for direction flag. Next comes interrupt flag. Interrupt flag determines whether the external interrupts like keyboard entry are to be ignored or to be processed. It disables the external interrupt when the value is reset, that is 0, and enables the interrupt when it's set, that's 1. Means if the given instruction is an illegal instruction or is yielding in an illegal value, then the value of interrupt flag will become 0 and it will ignore the instruction and moves to the next instruction. For example, divide by 0 is an illegal instruction, so it will ignore this instruction and moves to next instruction. For all the legal instructions and values, interrupt flag remains 1. Now let's discuss next flag, that is sign flag. Sign flag shows the sign of the result of an arithmetic or logical operation. The sign is indicated by the leftmost bit. The positive result clears the value of sign flag and the negative result sets the value of sign flag. Let's consider the following two examples. In this example, we are utilizing sum operator. So after any arithmetic and logical operation, you need to focus on the leftmost bit. This leftmost bit is known as sign bit. The value stored in sign bit is directly copied in the sign flag. So sign flag becomes 1. So this result indicates that the achieved result is a negative number. Let's consider another example. This example is again utilizing sum operation. So after arithmetic operation, the achieved sign bit is equals 0. So for this example, sign flag value equals 0. Next turn is of 0 flag. 0 flag indicates 0 result. This flag is set to 1 when the result is 0. For example, 2 minus 2 is equals 0. So 0 flag for this example is 1. Similarly, 0 flag is set to 0 when the result is a non-zero number. For example, 3 minus 2 is equals 1. So for this example, the value of 0 flag is 0. Let's consider few more examples. So example number 1. So for addition operation, 0 plus 0 yields in 0 result. So for this example, the value of 0 flag will become 1. Let's consider another example. In this example, we are adding two numbers. So after addition, we have achieved a 0 result. So it means in this example again, 0 flag is equals to 1. Let's consider another example. So let's subtract two numbers. If you see for this third example, the result is a non-zero number. So for this example, the value of 0 flag is 0. Next flag is auxiliary flag. Auxiliary flag indicates whether an operation produce a carry or borrow in the low order 4 bits. Do remember that 4 bits are considered as nibble. For auxiliary flag, when working with 16-bit values, we only consider the least significant 8 bits. To understand auxiliary flag, let's consider a few examples. So example number 1, let's add two numbers. If you have observed, a carry from lower nibble has been generated and moved towards the higher nibble. This transfer of data from one nibble to another nibble activates the auxiliary flag. So for the given example, auxiliary flag is equals 1. Let's consider another example for subtraction. Now here 0 minus 1 is not possible. So this 0 will request the next number for a borrow. So this one will become 0 and it will give its base as a borrow. So if you see that from higher nibble, we have transferred the data towards the lower nibble. So this will activate our auxiliary flag. So 2 minus 1, 1, 0, 0, 0, 0. So here again, auxiliary flag is equals 1. Now let's take another example of 16 bits of data. For this example, the achieved results will be you have observed that we have transferred data from one nibble to another. But specifically for 16-bit data, we need to consider only lower 8 bits in order to check the status of auxiliary flag. As there is no transfer between these two nibbles, so for that reason, the status of auxiliary flag will be 0. Now let's discuss parity flag. Parity flag indicates even parity of the low 8 bits of the result. Parity flag is set to 1 if the lower 8 bits contain even number of ones. Else the parity flag will be 0. For 16-bit values, just like auxiliary flag, only the least significant 8 bits are considered for computing parity value. For better understanding, let's consider the following few examples. So example 1, let's add two numbers. The result of given example will be, after obtaining the result, count the number of ones. 1, 2, 3, 4, 5, 6. If the number of ones in the result are even, then the parity flag equal to 1. So specifically for this example, as the number of ones are 6, that's an even number. So parity flag will be equal to 1. Now let's consider another example. Now let's add these two numbers. So the result will become Just like auxiliary flag, we will only consider the least 8 bits. The total number of ones in these 8 bits is 1. That's an odd number. So the parity flag will be equal to 0 for this specific example. In case if all the bits in the given result are 0, then still parity flag will be 1, as the number of ones in the given data will be 0 and 0 is an even number. Do remember, for every 0 flag equal to 1, parity flag is also 1. Now let's discuss the second last flag, that is carry flag. The carry flag records the fact that the result of an arithmetic operation on unsigned numbers is in range or out of range. To understand carry flag, let's consider the following examples. So example number 1, let's add two numbers. So the given question utilizes two input data of 8 bits. In case the achieved answer takes more than 8 bits, then the carry flag will be equal to 1. So for the given question, the result will be. So for the given example, the achieved answer is in 9 bits. So we are going to discard this bit and the value of carry flag will become 1. Let's take another example. In this example, we are utilizing subtraction operation. So the result will be 0. So 0 minus 1 not possible. So this 0 is going to take borrow from its base, that's 2. For this example, as the data is borrowed from outside of these 8 bits, so for this question again carry flag will be equal to 1. Let's discuss the last flag, that is trap flag. Trap flag allows setting the operation of the processor in single step mode. For example, the debug program we use sets the trap flag to 1, so we could step through executing one instruction at a time. Do remember that trap flag is set by the developer of the programming language. It means the value of trap flag is equal to 0 for C, C++, while the value of trap flag equal to 1 for assembly language. In order to test our understanding of all flags, let's dry run this program. Do remember, for dry run, we ignore initial and termination instructions. For the first instruction, that is move AL, 10, the value of AX will become 0, 0, 0, A, and BX will remain 0. Do remember, initially all the flags other than interrupt flags are 0. One more thing that you guys need to remember, that move instruction can only update register. It cannot update any flag. While all arithmetic and logic operations can update registers as well as flags. So next instruction is move BL, 1. So AX will remain same, while BX will be updated to 0, 0, 0, 1, and all the flags will remain same. Next instruction is sub AH, BL. It means subtract the values of BL from the values of AH and store the value in AH. So the value of AH is 0, 0. So in binary it will be, and the value of BL is 0, 1. So in binary it will become. As we can see, 0 minus 1 is not possible. This 0 will ask for a borrow from the next number, which again is not possible. So this borrowing request will go on and it will reach the end. So now the last 0 will take the borrow from its base, that is outside of this 8-bit of data. So for this reason, carry flag will become 1. So now this base will be given as borrow to the required destination. Now as you see that the data from this nibble has been transferred to this nibble, so the auxiliary flag will also become 1. So the result will become, so as the instruction has been solved, so it means interrupt flag is equals 1. Next comes the sign flag. So the leftmost bit is our sign bit. So copy this bit and paste it in the sign flag. As the answer achieved is a non-zero number, so zero flag will be equal to 0. For parity flag, count the number of ones in the answer. So total number of ones in the answer is 8. So it means the parity flag is equal to 1 as 8 is an even number. For overflow flag, first we are going to check the operation, that is subtraction, and then we are going to check the sign bits. If you remember, for subtraction operation, both the sign bits of the data must be different, but over here both the sign bits are same, so it means overflow not possible. So overflow is equals 0. As the destination was AH, so it means there will be no effect on BX. And similarly, there will be no effect on AL. The answer will be stored in AH, so the answer will become FF. Moving to next instruction, that is add AL comma AH. So the answer is going to store in AL. So copy paste the value of AH and copy paste the value of BX. Now, the value of AL is 0A. So 0. And the A means 10. The binary of 10 is 1010. And we are going to add this with FF, that are all ones. Let's add. So this will become 1, 0, 0, 1, 1. Again, the data has been transferred from one nibble to another nibble. So that's why auxiliary flag is equals 1. So it will become 0, 0, 0, 0, and one extra carry has been generated. So this means that carry flag also equal to 1. Now count the number of ones, that's 2. So parity flag also 1. As the answer is non-zero, so 0 flag is equal to 0. The leftmost bit, that sign bit, is 0. So copy sign bit and place it in sign flag. As you have solved the instruction, so it means it was a legal instruction. So interrupt flag equal to 1. Now for overflow flag, specifically for addition operation, both the sign bits must be same. But over here, both the sign bits are different. So overflow flag is equals to 0. Now for answer, the answer will become 0, 9. So we will update the value of AL to 0, 9. Now next instruction is move AX, 0xFFFF. Do remember that this 0x means hexadecimal number system. So for move command, as we have discussed earlier, that all the flags remain same. So copy and paste all the flags. Now as we are updating only AX, so it means BX will remain same. So AX will be updated to F, 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 F. Now let's move to the last instruction, that is exclusive OR AX, AX. Do remember, if you are applying XOR operation to the same data, the achieved result will always be 0. So exclusive OR AX, AX means that we will achieve all zeros in AX. So AX will be updated to 0 and BX will remain same. Now as this was a legal instruction, so our interrupt flag will be 1. Now for simplicity, as our answer was 0, so 0 flag will be equal to 1. And as discussed earlier, for every 0 flag equal to 1, parity flag is also 1. Other than interrupt, 0 and parity flag, all remaining flags will be 0 for this given instruction. In order to evaluate your understanding of flags, you can solve this task in your free time.